Bismillah ar-Rahman ar-Rahim. We have matrix X. It is an n by n square matrix that is Hermitian and positive semi-definite. It has a rank R. X can be eigendecomposed. We can write X as a matrix of eigenvectors psi, and then we have a diagonal matrix of eigenvalues. The eigenvalues are real valued and non-negative. We have R strictly positive eigenvalues, and the remaining eigenvalues are equal to 0 because the rank is R. Then we have here psi Hermitian. We can write down this eigendecomposition as a summation k from 1 to R, and then we have lambda k. And if this psi has the columns psi1, psi2, and so on, this will be psi k Hermitian. If we define qk as the square root of lambda k psi k, then this summation here can be written as summation k from 1 to R, qk Hermitian. So we write X as a summation of R rank 1 matrices. Each matrix here is an outer product of vector qk. Our goal here is to find a decomposition of X that looks like this, but we also need to satisfy a bunch of constraints. Those constraints are related to another matrix A. A is a Hermitian matrix. The inner product between A and X divided by the rank of X is alpha. So alpha is the trace of A Hermitian X over R. And because A is a Hermitian matrix, this is just the trace of AX over R. We want to write down X as the sum of rank 1 matrices, but at the same time, each vector here, when it is involved with matrix A in a quadratic form, the quadratic form must be exactly equal to alpha, which is the inner product divided by R. So this must be true, qk Hermitian A qk equal to alpha for every k in the set from 1 to R, where R is the rank of matrix X. Note that the trace of AX is the trace of A, and then we can write down X as the summation of rank 1 matrices. Trace is linear, so this is the summation of the trace of each of those matrices. Then we can use an important property of matrix trace. If we have two matrices, C and D, this guy is n by m, and this is m by n, then the trace of CD is equal to the trace of DC, which means that we can swap. We can think of this as one matrix and this as another matrix, so we can swap these two guys. Now this is a quadratic form. It is a scalar or a 1 by 1 matrix, so the trace of this is just qk Hermitian A qk. And if we want each of those terms to be equal to alpha, then this is alpha added to itself R times. That is, this summation here is alpha R. So given X and given A, we have their inner product. We want the inner product to be the sum of R terms. Each one of those terms is exactly equal to alpha. How can we decompose X obeying those constraints? The first step is simply to ignore the constraints and to write down X as a sum of outer products using, for example, this eigendecomposition or any other method. So initially, we ignore those constraints. Then our procedure will be to modify those Q bar vectors so that those constraints are satisfied. If QK bar Hermitian A QK bar is equal for every K, then this is actually what we want to achieve, and we are done. Suppose that there is V between 1 and R such that Q bar V Hermitian A Q bar V is greater than alpha. So it is alpha plus delta, and delta is positive. Note that this summation is equal to alpha times the number of terms, which is R, the rank of X. So if there is a term that is strictly greater than alpha, there must be another term, let's say Q bar S Hermitian A Q bar S, that is less than alpha. So this term is alpha plus gamma, and gamma is negative. We can have it the other way. It can be the case that Q bar V Hermitian A Q bar V is alpha plus delta, and delta is a negative number, meaning that this quadratic form is strictly less than alpha. Then there must be another quadratic form that is strictly greater than alpha. So the idea is that this is equal to alpha plus delta, this is equal to alpha plus gamma, and delta gamma is a negative real number, which means that delta and gamma, they have the opposite sign. How can we start from this and do modifications to the Q bar vectors so that we satisfy the constraints? The idea is that we will replace this Q bar V vector with vector QV. Vector QV is a linear combination of Q bar V and Q bar S. Specifically, it is Q bar V plus eta Q bar S divided by the square root of 1 plus eta squared. Eta is a real number. And before explaining what eta is, vector Q bar S is modified to minus eta q bar v plus q bar s divided by square root 1 plus eta squared. So this vector will be replaced by this quantity here. And the vector q bar v will be changed to this qv, and that's it for this vector. This vector will be fixed now. So what is eta? Eta is a real number that is chosen so that this vector qv satisfies the required constraint. So eta is chosen such that qv Hermitian A times qv is equal to the required alpha. Now the question is there any eta that will actually do this? And the answer is yes. Write down qv in terms of q bar v and q bar s and this real parameter eta. So here is the quadratic form that is required to be equal to alpha. We get here a factor 1 over 1 plus eta squared, move it to the other side. So the other side will be alpha times 1 plus eta squared. And then expand this side, it will be 4 terms. We will have q bar v Hermitian A q bar v plus eta squared q bar s Hermitian A q bar s plus eta, and then we have the cross terms. So this will be q bar s Hermitian A q bar v and the complex conjugate. Note that this quadratic form here is alpha plus delta, and this quadratic form here is alpha plus gamma, where delta and gamma are non-zero and they have the opposite sign. Their product is a negative real number. If you replace this quadratic form by alpha plus delta and this one by alpha plus gamma, then we find that there is alpha on both sides and there is alpha eta squared on both sides. Eliminate. Then we end up with the quadratic equation in eta squared, specifically eta squared times gamma plus eta times this. So here we have a complex quantity plus its complex conjugate. This summation I will call H sub SV. And this is a quantity that can be computed because we know the q bar vectors from our first step when we do the decomposition of matrix X without paying attention to the constraints. So we know those q bar vectors and we have matrix A. Let this summation be H sub SV, and this is multiplied by eta, and then we have this gamma here. That's a quadratic equation. What is the solution to this quadratic equation? The solution is minus HSV plus or minus square root HSV squared. Note that HSV is real because it is a complex quantity plus its complex conjugate. And then we have minus 4, and then we have gamma delta. And here is the good news. This product is negative. So under the square root, we have a non-negative real number. So we can take the square root without getting imaginary parts. And then we need to divide by 2 times gamma. There are, in fact, 2 values for eta such that this constraint is satisfied. And so now we have one of the quadratic forms is made equal to alpha. But note that we have changed the vector q bar v to the vector qv. Recall that X is summation k from 1 to r of q bar k Hermitian. So it is a summation, and there is a term here q bar v Hermitian, and there is another term which is q bar s Hermitian. So what did we do? We took this and we changed vector q bar v into the vector qv, which is given by this linear combination of the 2 vectors q bar v and q bar s. Those 2 vectors were chosen because the quadratic form involving one of them was greater than alpha and the other quadratic form was less than alpha. So what we did is that we changed q bar v to qv, and now this is satisfied. But this now is changed to qv Hermitian. But we want the summation after modifying our vectors, after modifying our rank 1 matrices, we want the sum to remain equal to the given matrix X. So we need to change also the vector q bar s so that q bar v Hermitian plus q bar s Hermitian is equal to qv Hermitian plus q bar s modified Hermitian. And we need to modify q bar s using this linear combination of q bar v and q bar s minus eta q bar v plus q bar s, and this is divided by the square root of 1 plus eta squared. And here we have a formula for eta. We can check that this will do the trick for us. If we take qv Hermitian and q bar s modified Hermitian, then we will get the two terms that were originally there in the decomposition of matrix X. So by modifying the vectors, we are keeping that our summation, our decomposition is exactly equal to matrix X. We had this summation here, and it is equal to alpha r. After our initialization, one of the quadratic forms was strictly greater than alpha and another was strictly less than alpha. We did a modification such that now one of the quadratic forms is exactly equal to alpha. And we did so preserving that when the vectors are changed, this summation remains as is. It remains as our given matrix X. At most, we need to repeat this step r minus 1 times to make corrections and make all the quadratic forms equal to the desired value alpha, which recall it is the inner product of the two given matrices X and A divided by the rank of X. So here's a code. This is, a silly code. It's not optimized or anything. This is matrix X, and matrix Q is Q bar 1 to Q bar R. This is at the beginning. Alpha is computed. Here we compute the quadratic forms minus alpha. Okay, and so, to know which of them is greater than alpha and which of them is less than alpha. So here we compute Q bar K Hermitian A, Q bar K minus alpha for K from 1 to R. And then we take the first vector here. We take this vector and we find the sign of Q bar 1 Hermitian A, Q bar 1 minus alpha. This will be positive or negative. Now we search for another vector which gives a different sign. So if this is positive, then the other vector gives negative and vice versa. In other words, we want, if this quadratic form is greater than alpha, we want another vector with a quadratic form that is less than alpha or vice versa. And then we do our modification. We compute eta and we modify the first vector. Now for the first vector, this difference here will be 0 after the modification. We also need to modify the second vector. Remember that we want the sum of the outer products, the sum of the rank 1 matrices, to always be equal to the given matrix X. So we need also to modify the other vector and modify the difference of its quadratic form minus alpha. Then we go to the next vector here and so on. At most, in r minus 1 steps, we will modify the vectors and get X as a summation, K from 1 to R, QK Hermitian, and at the same time, for every K, QK Hermitian A QK is a constant, the constant that is equal to the inner product of A and X divided by R.